squared divided by that.
L is assumed constant.
Does the number of sites on a catalyst surface change?
No.
Remember, these aren't empty sites, these are just sites. So it's not much of a catalyst if that's changing. Now that is a mechanism of catalyst deactivation. Imagine that I have two small particles and they grow to make one larger particle. Have I lost sites? Have I lost atoms? Let's start there. No. Conservation of mass means that if I take two balls and I make one big ball, I have the same number of atoms. Have I lost sites?
Yes.
Why? Because, yeah, the surface area per atom is changing, right? If I have a very, very large particle, then the number of atoms at the surface of that particle is small compared to the total number of atoms. If I have a single atom, they're all at the surface. So those are sort of two extremes that you can imagine, right? A single atom, all the atoms are at the surface. Metal particle that's about 10 nanometers large, only about 10% of the atoms are at the surface. So when you grow, you lose sites. But again, that's deactivation. We're not worried about deactivation right this second. So we use that definition for star related to the number of total sites.
What would that look like in an equation? Is that like A star plus A star equals B star?
What are you asking about?
When you put the two balls together?
I mean, you wouldn't put it in an equation, but there is, in that case, if it was a continual process, or you had many particles that are agglomerating at different rates, it just means that this is not equal to 0.
No, what I'm saying, like, it only happens when you're like absorbed to the catalyst that they fuse together.
No, I didn't say that. Just heat it up, and the two particles, these aren't adsorbates, these are metal particles. These are catalysts. And this is a support. So this is, it's called sintering. It's, you take metal catalysts and you heat them up, they get bigger. And that means that you lose catalytic active sites. But again, barring deactivation, this is true. The number of sites aren't changing with time. And so what you end up with is K3 times big K1. Wait, hold on. All right, let's also assume now I'm only doing this to simplify the equation, otherwise it's half the board to write. So the rate that you end up with is K3 times the adsorption equilibrium constant for A and for B, so steps 1 and 2, times the concentration of A, the concentration of B, divided by 1 plus concentration of A, So this is the numerator. This is called a Langmuir-Hinshelwood rate equation. I'll write that out. This uses the same assumptions as Langmuir, as the Langmuir isotherm for adsorption. Okay? Now it's just applied to a reactive system, so that's why Hinshelwood shows up. Usually it's just abbreviated LH.
Where does the L go?
So I guess it would make more sense to put a prime there. I was going to do it in the next step but the L ends up in the pre-exponential factor for your rate constant. And often though, you'll pull one of the L's out because you're actually, a lot of times you're trying to solve for this. So what's the difference between these two things, first of all? So what are the units here? Moles of reaction per time. We know that much. But is this, do I put a volume here?
Everything's under concentration, so evaporates into concentration.
It's catalysts. So yeah, we don't normalize by, this isn't the volume, this is volume of the reactor. So these unit conversions also end up in your rate constant. But what you have here is, often you'll have kilograms of catalyst, right? That's what we've been using when we've been working with PBRs all semester. So let's just think about this for a second and see, is this a good choice? So imagine I had a catalyst, palladium on carbon. Okay, so carbon is a very common support, palladium, precious metal. And I have one that's 1 weight percent palladium, and I have another that's 10 weight percent palladium. Let's assume that the particle sizes are identical and everything about the catalyst is identical, except one has just a few particles and the other has 10 times that many. Would you expect that the rates would be the same on those two materials? Would it make sense to you to normalize by kilogram of total catalyst when 90 to 99% of the weight is an inert carbon material? Yeah.
40 kilograms of catalyst refers to your kilograms of palladium. That's the actual catalyst.
I don't know.
Well, mass.
If I'm reading a paper and they say kilogram catalyst, I got no idea. I could read 10 different papers and half of them are going to be talking about what you're saying, the mass of the active site. The other half are going to talk about they took some catalyst, they put it on a scale, and that's what they got.
So what is the convention? Direct catalyst referring to the whole particle or just to the palladium?
If I see catalyst, I'm generally thinking the entire particle, yeah. Because you could also write mole per second times what? Kilogram of palladium. If they meant palladium, then just put palladium. And you'll see that too in papers where they'll normalize by the mass of their active material. But now let's go back to this picture and let's imagine that I have this material, and I'll let you know, we'll say that 50% of palladium is at surface. And in this material, it's only 30%. These numbers, by the way, are called dispersions. So one material has a dispersion of 0.5, the other material has a dispersion of 0.3. You can estimate particle size from dispersion using a very, very simple just 1 over the dispersion. So these particles, if you like thinking in terms of percent at surface, these particles are about 2 nanometers. These particles are about 3 nanometers. Okay, so I've centered my particles. Now I have the same weight loading, so forget the weight loading bit. Again, does it make sense to normalize these by mass of catalyst if I want to know, does the palladium behave any differently? What's a better normalization then?
Maybe you can say that, like, because stuff's only gonna react what's on the surface of the catalyst.
Right, so instead of using the total mass of my active material, normally at this point you switch to moles. I'm not quite sure why, probably just because the mass is extremely small. Palladium at the surface. And that's fine. We can convert between all of those things. If I know the mass of my catalyst, I know the molecular weight, so I get the moles of palladium. I know the dispersion, so I just multiply it or divide it, I don't know, by the dispersion, and you get the amount of surface palladium atoms. This, in these units, is referred to as a turnover frequency. It's a rate, so it's a frequency, right? And it's referred to as a turnover. So what is a turnover in catalysis? What does that mean?
Just the number of molecules reacted per time.
Yeah, so you can think of like, what does a turnover mean? It means that the cycle has closed, right? So in other words, I started with empty sites, I end up with an empty site. So it's going all the way through the mechanism and then finishing. Yeah.
So the amount of palladium that's active is a percentage of the weight percent of the total catalyst. So it's
Right.
like 2 percentages.
Yeah, exactly. If I make a material, a lot of times, again, part of the reason why we put it in contact with these supports, one is for surface area reasons. We don't want a giant palladium boulder because very few of it's on the surface in that case. We want really small particles, so we put them on a material that makes that possible. The other is to save money, right? You know, we don't need to make 100 weight percent palladium. It wouldn't work very well. So yeah, these are typical numbers. You know, 1 to 10% is common. So that's the weight of the material. So if I've got 5 grams of catalyst, in the 10% case, half a gram is palladium. But then of that palladium, only some of it is dispersed to the surface of the particle, right? And that depends on how many